zoom in on the region that we have data for. So you could set the x limits to can be 270 and 400. That's where we have data. And you end up with a plot that will look like this. You can see that it's a lot easier to see where the data is. The next thing you need to do is calculate the extinction coefficients. So do you remember how to do that?
Beer-Lambert, but rearrange.
So Beer-Lambert is the extinction coefficient times the concentration times the path length. So the extinction coefficient is the absorbance divided by the concentration times the path length. Right, my mouse. So you can see here I've written this equation in here, and it's got these dollar signs on it. Does anyone know what the dollar signs do? Pardon? Is that what it's technically called? It may well be an array multiplication. I have no idea. The important thing for me is that it keeps yeah, perfect. It's an absolute reference. So if we get rid of them, then we can drag this formula down like this. Oh, I need to delete my we can drag that formula down like that, and we get all these divide by zero errors. Because as we're moving down, we've got B5 times B3, B6 times B4, B7 times B5, so on and so on. And we don't want that. So the dollar signs keep the cell reference static. So as we drag it down, we'll always get B5 times B3, no matter where we are. So that's just how to use Excel to make that as easy for you as possible. So you get all of those extinction coefficients, and you plot a graph of the extinction coefficient. The same basic rules as above, but this time you'll need a unit on the y-axis as well. And then you do all of that again for butanol, and you get a slightly different spectrum and a slightly different plot of extinction coefficient values. And then you're basically done with the pre-lab tasks. So if I just stop sharing, we'll go to a whiteboard and we can talk.